we've already seen a couple of these. These are special external evaluate cells. As you can see, they look a bit different to regular cells. The way you do them is in a brand new cell. So, my cursor is between cells at the moment. If you type the greater than symbol, it will automatically, so that's this symbol here, it will automatically create a new cell. And this cell won't necessarily be Python. I believe Python is the first choice, but it has all of these other languages as well. So R, for example, is another very common open source language out there for data science, used quite a lot in universities. So what this enables me to do is to just run Python code straight in Mathematica. It's possible that you need to do some initial setup. So it's possible you might need to connect to a Python kernel. So you'll need Python on your machine. And we'll see a bit later when we're connecting from Python back to Wolfram language, you'll need a Wolfram kernel on your machine as well. So you'll need to have purchased Mathematica for that to work, which, makes sense. But anyway, as you can see, I can just write some Python code and it'll just run in Mathematica, which is really, really nice. So I don't have to worry about, making sure, I don't have to worry about Jupyter notebooks or making sure I've got some files in the right place. I don't know. It's just, if I've got Mathematica open, I can just run Python code. I will say one word of warning, something which catches me out, actually, is that this code is running as if it were in the location of your Python directory. That means that if you run some code to say, if you run some code with the, OS library, then it's going to do everything assuming, everything is going to be related to that directory. So if you try to say, import something, for example, if I were to, I'm currently here in this notebook here. If I were to try and import this data here, I won't be able to just say, look in the current directory, because it won't know where I'm looking, because it's not here. This Python code is not running in this directory, it's running elsewhere. So that's something to be aware of. Anyway, so this is actually, behind the scenes, this is an external evaluate cell. But if you want to, you can actually write external evaluate explicitly like this, and in the first argument, state the language you want to use. So I want to use Python. And then you follow that with a string, and that string just contains Python code written as you would normally. And in this case, if I don't put this normal at the end, then I'm going to get a sort of Wolfram interpretation. So this may not be familiar to you if you're a Python user. This is just a particular case where it's tried to be smart and it has given us a sort of compiled version, I guess you could say. So I'm turning it back into a regular list. And yeah, the benefit of using external evaluate is that because this is just a string in the second argument, whatever you can do to strings in Wolfram language, you can do right here. So I can string join a number. I can actually insert a number, a bit like an F string in Python. So in this case, this is going to range up to 10, so 0 to 9 in that case in Python. So yeah, it's quite nice. Another nice thing about Python cells, in just cells generally in Wolfram language, is that what we have here right now is what we call a session. So whenever we run, if I say a equals 1, if I open a new notebook, if I were to say, a equals 1 over here and evaluate that, and then go back to this notebook here and say, what is a? Well, a is 1. We are in the same session. And the same is true for Python cells. So if I were to go back to my other notebook, I believe if I were to ask for list, there you go. List is still 0 to 9. So it still remembers it over notebooks. And the way to get around that, if you don't want that, you can quit your session. But I'm not going to do that here because obviously I've evaluated a bunch of stuff that I want to keep. But if you were to run this code, then this, then this list would come out as empty, nothing, because the session has been quit. So this is basically what I've already discussed. I guess further than just adding strings like I've done here, you can actually add some code. So in this case, one sort of way to get around the fact that the Python cell doesn't, this Python cell here wouldn't know how to find the current directory very easily. One way around that is to insert Wolfram code, because obviously my Wolfram code knows where I am. It knows exactly where I am. So if I insert that, then it's just a convenient way of getting around that particular issue. And in this case, what I've done here is saved a file and then loaded it, and that file exists here, just in case you're interested. I have already populated this folder with all the files we may or may not generate today, so don't worry if for whatever reason some of your code doesn't run. You've already got all the files. Right then, so I have gone into quite heavily into a comparison between the two languages. Now I'd like to go into more about how we can actually go from Python to Wolfram Language. So I've already gone from Wolfram Language to Python a bit. Now we're going to go back the other way. And the way we do that is using the Wolfram client library. So I'm just going to open that link. So we have documentation for that and how to install it with pip. So we've got a lot of stuff there for you, just in case you want to know how to do it. So I'm going to be going over some of the examples in here today, or at least similar ones. So this is just a library like any other, so we're going to see some similar syntax as we've already seen. So I'm going to first open the first Jupyter notebook. So that is this one right here. All right, so basic usage. So perhaps not this particular notebook, but certainly the ones following, you will need to have got Mathematica installed for the Wolfram language code to actually produce an output. So without a Wolfram kernel, you can still run the code, like you can still produce Wolfram language code from within Python. It just won't evaluate. So if I import the library and import WL and WL expression, let's see what they do. So WL select is literally just the Wolfram language select function. That's it. That is how you use Wolfram language functions in Python. You import this library and you just say WL dot such and such function, and there's nothing more to it. That's literally it. So obviously they are uppercase because they are in Wolfram language, but otherwise you can still just use regular Python syntax, hence the the sort of curly brackets here, whereas they would be square brackets in Mathematica, and then print the results, and this is what you get. You get Wolfram language returned. So you'll notice it's not actually doing anything, but if I were to copy this, go back into Mathematica, paste it, and then evaluate, I get my result. So that's because I'm connected to a Wolfram kernel here, whereas here, I've not specified that I've not started a session or anything. I've just simply asked it, what is the Wolfram language for this thing? And it has given me a result. Now, that's WL. That's sort of the way to say this. I want to extract this particular function from the Wolfram language. But what if there is no function for what you want to do? So it might be an anonymous function, for example, or it might be an entire expression of many functions, and you can't be bothered to write WL.function1, WL.function2, and you just want to write Wolfram language code and inject it into your Python. Well, for that, you can use WL.expr, i.e. Wolfram language expression, and then wrap that around a string, and then in there you can put anything you like, any Wolfram language expression, and this is Wolfram language syntax now, so that we're talking square brackets, things like that, and that will also work. And so in this case, there's no difference, it looks the same, but you can imagine that this might reformat to something else. So if I had done a condition, for example, I'm just picking this function because condition has a shorthand that looks like a forward slash and semicolon. So it might have reformatted to appear like that instead of the whole word condition. Anyway, slightly sidetracking there. So how do you actually evaluate Wolfram language code? Well, you need to start the session. We will look at cloud sessions momentarily, but for the moment, we'll just look at a desktop session. So for this, you need evaluation, and we can import a Wolfram language session, and this is just a standalone function that you just evaluate. And from now on, I will be able to, my session has begun, and I will be able to evaluate code from within Python. Now, you might need to enter a specific file path to actually tell this Jupyter notebook where the Wolfram kernel is. So it'll be something like, users, then your username, then Mathematica / Wolfram kernel. It'll be something like that. But in this case, I shouldn't need to. There you go. So now that it's started that session, so there's going to be some overhead because it's starting it for the first time. But now that it has started that, I can simply use evaluate to evaluate something. And we already gave x a value. X is equal to the selection from the range 1 to 10, all those that are prime. So if we now go down to here, our answer is the numbers 2, 3, 5, and 7. And I suppose I should be able to just wrap print around that, and it'll probably remove the packed array, I would suspect. Let's see. There you go. Okay, so there you go. So that is our output. And we can evaluate y and z as well. So for the remainder of this notebook and serialization, it's going to get a bit confusing, certainly for me, where we're going to have a mixture of Wolfram language and Python syntax. So forgive me if I make a mistake, but it does get a little bit confusing when you start just mixing the two. So anyway, in this case, let's see, if I just run that. So in this case, I have exported a bar chart to a particular location, and that would be, if I just go and grab that now, that would be this bar chart here. And you'll notice that although I'm using a Wolfram language function here, bar chart, the syntax is still, even within that function, Python syntax. So this is not how you do options in Wolfram language. So if I were to grab this code and go back to Mathematica, first of all, we need square brackets here. But second of all, this should not be an equals. It should be a hyphen and then a greater than symbol to make an arrow. And then finally, this should be curly brackets for a list. So the whole thing is Python syntax. Let's just add some data and see what happens. There you go. Nice little bar chart there. Anyway, so this is all well and good, but what we'd like to actually do is actually visualize the image within Python without having to go back to Wolfram language. And so for that, we can actually sometimes use some other libraries to do that. In this case, the pill library. So there you go. I guess I didn't change the data. Oh, okay. So the data just flukily happened to be very similar between those two examples. And of course, we can apply some computation to that before we do our export if we really want. But I mean, why would you do that? That's just not very nice looking at all. Anyway, so what I think a big part of why you might want to use Python and Wolfram language together, a big part is the functional programming aspect of Wolfram language. And what I'm going to show you now is how to actually define a language, within Python using some Wolfram language code. So the first way to do it is to simply define a function as you would, normally in Python, but just use some wl.functions. So in this case, I'm defining a population density function. I'm having to use session evaluate because I'm going to be using some Wolfram language in there. And then I'm just doing wl.quantity magnitude, wl.divide. So it's all sort of Wolfram language-esque code, but using Python syntax. So that's one way of doing it. I would say this is probably the method I would use if I'm not going to be using many Wolfram language functions. So some really helpful ones are the entity functions. So we have within the language these things called interpreters that enable us to interpret, essentially fuzzy stuff. So we use a bit of machine learning in there. So I want to interpret this as a number and it gives you an actual number. You want to interpret this string as a semantic number and it gives you that. So it can interpret stuff with a bit of fuzziness, which is really useful and something that might not exist within Python. And things like population data. So if you want the population of France, rather than having to pull some data from the internet somewhere, we have that built into our Wolfram knowledge base. So that would be quite a useful bit of functionality there. But generally speaking, I wouldn't recommend using WL. If you've got loads of functions. For that, I would use a Wolfram expression. And in this case, I have an entire chunk of Wolfram language code. I might not know how to write it in Python syntax. Not to worry, I'm just going to write my code directly. So in this case, this function here is pure, it's actual pure Wolfram language code. So if I go back into Mathematica here, if I evaluate this and then say, what is the population density of France, say, there you go. That's the answer. So, it works. And it should also work here. I'm not saying it's going to be fast. So as with anything like this, I would recommend, this is not the sort of thing that you want to be having running on the fly. You would probably want to use this once to import a load of population data and then, export that somewhere. Not so important. Okay, so one final thing to mention is that these sessions actually use Wolfram kernels, but essentially you can run things on multiple kernels at once, so as to run things in parallel. Well, each time you have a session, it opens a new kernel, and you don't want to leave that lying about because you only have something like maybe 4, 6, or 8 kernels available to you, and so if you just leave them all open, eventually you're going to run out of space, and your code won't run. So it's the sort of thing that should pop up in your task manager. It's something like this. So apparently I have 2 versions of Mathematica open, okay. But if we look here, I have 2 Wolfram kernels open, as far as I can tell. So anyway, I am going to actually terminate my current kernel. Okay, so that's just the basics of injecting some Wolfram language into your Python code. Now for the more confusing part, which is serialization and deserialization. So this is sort of all about showing, actually evaluating Wolfram code and then displaying it as Wolfram code rather than as a Python output. It's a bit of an odd thing to do, to be honest, but it can be done, and you can export into different formats. So what you do basically is you import the export function and the binary deserialize function from the Wolfram client. Again, there's going to be more about this. Let's see if I can find the particular tab. So again, there's going to be more about this in the Wolfram client library if you want to look at it. So here we have serialization, for example. So it's all explained there in more detail if I don't do a very good job today. All right, so in this case, I'm exporting a Python list into a target format, which is WXF, which is, as far as I know, it's a special Wolfram language export format, compression format. And what I can do is if I print my list as that, then I get this, which is just gobbledygook. But if I deserialize it, then I get back into a nice Python list. So yeah, as I said before, it gets a bit confusing when we start mixing Python and Wolfram language. But in this case, by using export, I've taken what is essentially Python syntax injected with some Wolfram language functionality, and I've turned that into a Wolfram language expression. So yeah, it's a bit odd. And you can do the same for things like images, There's, let's see, arrays, data frames, for example, so data sets. So this pandas data frame would look like this in pandas, but in Wolfram language it comes out as a data set of associations. Just in case you're not aware of what that looks like, in the Wolfram language we have these things called associations, which are essentially like dictionaries. They are keys going to values, and sorry, and data set is a special function which takes that and converts it into a nice table. There you go. So it makes it all nice and pretty. Anyway, so yeah, it's all a little bit confusing, but yeah, that is what you can do with our serialization and deserialization. So I think I'll move on to cloud connections, because somebody mentioned APIs earlier. So yes, in Wolfram language you can create APIs very easily. I'll just show you how you do that within Wolfram language first. So with that, the way you do it is using API function. Whoops. I'm attempting to go to the documentation then. So, okay. So, API function, if you spell it right, is a really easy way of creating your own API. And just to get so API functions will work on desktop as well as cloud. You know, they're designed to be online things. So an API is, to answer your question, is a bit like a function that works online and that anyone could use. So in this case, it might take a whole number, an integer, and it might add 3 to it. And so if someone was to go to your URL and say, you know, input the parameter 1, then your API would spit out the answer 4. So it's a bit like this sort of online function that you've sort of put on the web. And APIs are not just used for functions like that. You know, for calculations, they're also used for grabbing data. So you'll get APIs for a lot of websites. So rather than so a lot of websites, rather than actually pulling data from a sort of a data set that they own, they might actually have something, you know, owned by some other company, and they pull that data via an API. A lot of websites like Facebook, Twitter, you know, they have APIs. And in fact, speaking of, we have very special API set up for particular services. So, you know, we have a selection of services in this list here. So Twitter, LinkedIn, Facebook, whoops, Reddit, you know, all of these are specially connected so that it's even easier to connect. So these all have their own APIs, but not only that, we allow you to sort of connect. We've sort of got this outer wrapper called Service Connect that allows you to do it, you know, even easier than you would normally be able to do, because using APIs is designed to be easy. So yeah. Anyway, so going back to APIs, you can use them on desktop. So in this particular example, there's an API function that takes an integer, adds 3. You insert an association to say, let the parameter be 5. 5 plus 3 is 8. 8 is what comes out. But also you can deploy them to the cloud. Very easy to do. You just use cloud deploy. And in that case, you can actually start using the API. So if I just grab this particular example, because it's a fairly simple one. So in this case, I don't need to give it a name. So in this case, if I create an API where it takes an integer and it finds the factors of that integer, and then I deploy it to the cloud, assuming I am connected to the cloud. So I mean, it turns out I am, but in case you are not sure, there is a function to tell you whether or not you're connected. Anyway, if I go to this URL, it's probably private by default. Yes, it is. This is going to be embarrassing when I get this wrong. Oh no, what is going on there? Oh, of course, because we haven't got an input. So what I can do I believe I can put in a default input there. Let's try that. There you go. So in this case, it's really easy. I've said x is an integer, default is 1, and so the answer, the factors of 1 are 1 and 1. If I were to do something like a default value of, I don't know, 64, that should give me a lot. And now, of course, it's a power of 2, so it's giving me the simplest amount. It's not all the factors, it's just simply a prime factorization. So it's simply saying 2 to the power of 6. Not the best example in the world. But the idea is I should be able to say x equals 10. I'm hoping this is the right syntax. Why is that capitalized? There you go. If I say x equals 10, then I get that 10 is equal to 2 times 5. So you can do this yourself and create your own APIs really easily. But the idea is that adding to the URL like this is cumbersome. Wouldn't it be better if we could do it some other way? And so APIs on the web will have things like input fields where you can type in stuff, or it might be simply a button. And you may or may not have noticed that some URLs actually do change just like this. Not always desired, because that means that if you have a website where it says something like user access equals false and the user just changes it to true and it allows them access, that's bad. But generally speaking, APIs may well change the URL like this. Anyway, I'm sort of digressing here. So if you want to set up APIs via Python, then you're going to need to set up some authentication. This is not required if you just go via Mathematica. This is purely because we're in Python now, I'm afraid. So I happen to have some example keys here already set up. Here are some I made earlier. So this is actually really easy for me. I can just run this and it just works. But for you, you may well need to go to this documentation page and set up your own secure keys using this function here. So it's still really easy, but I happen to have already set mine up. And now that I've got my cloud session set up, so this is, remember we had our sessions before that were Wolfram kernels. Well, now our session is a cloud kernel. So I've started my kernel and it's authorized. Sorry. And now I can just run it like I would, any other kernel. So it's going to take slightly longer because of that cloud connection, going to and from the cloud. And I suspect that there will be some limitations on the amount of stuff you can do on the cloud. So the Wolfram Cloud is, generally speaking, a free version of Mathematica, but it's on the cloud. And I guess because it's free, it's limited in some way. So just be aware of that. But for simple computations, it'll do the trick. So in this case, I'm just asking for the numbers 1 to 3, and there you go. There's my list back. And so unlike a desktop kernel, the cloud doesn't sort of remember. Things don't persist. So if I say let x equal 1 and then ask for x back, it doesn't recognize it. So it recognizes it here as a global symbol x. That just means, it has no value. So you can ensure things persist, but you'll probably want to create them as functions in order for that to happen. So in this case, I'm creating a function that takes the reverse of a string, and in a brand new cell, I'm asking for that function, and it has remembered it in this case. So moving on to APIs again, but this time some I've made earlier. We're going to actually look at some that actually do a bit more than just do x plus 3 or factor integer, whatever I was doing before. So I've created two. One is a single parameter, really simple one, and you'll notice these are just raw text, raw sort of cells, and that's because I've already evaluated these beforehand. Sorry, and I don't need to evaluate them again. But essentially, I ran this code in Mathematica. So first, I connect. This is an optional step. If you are already connected to the cloud, then you won't need to do that. By the way, just in case you're interested, yes, you are typing a plain text password in here. So I'm, personally speak, I would say that if you want to log into the cloud, I would, go onto the cloud and just log in there. I would personally feel better about that. But just so you know, obviously, Wolfram doesn't store any of your passwords or any of that junk. It's completely on your own machine, so you don't have to worry about that. So in this case, this single parameter one is just basically the same as before. We're just taking a number, and in this case, we are squaring it. And then in order to get it on the cloud, we just do cloud deploy of our API. And in this case, I've actually given it a name. So you'll remember for my earlier APIs, if I can find one, the URL is just completely nonsensical, but you can actually give it a name. So in this case, my URL will look like danielr/API private x squared. And what makes it private is the fact that I have not set public permissions. So in this case, if you are to access this API from within Python, you can read and execute code. But I guess if you were to try and access it via the web, you wouldn't be able to see it. So things are private by default, I believe. However, we can also make things public by just adding permissions goes to public. And that's what I do with the majority of my stuff, because it doesn't really, haven't really got anything to hide. So in this case, I've actually got that classifier we created earlier, and I'm turning it into an API. So this is my Titanic function, and I'm taking in the parameters, so the class, the age, and the gender, and with any luck, we should be able to now access that API. So now we're going back into some Python. So here is the name of my API. So this is what the URL will look like. It will look like your username and then this. And let's call it. Let's see what happens. See if it works. There you go. So according to this, according to my API, if somebody was in first class, 20 years old, male, chances are they probably survived. Now, this is obviously not telling me anything about the probabilities. I haven't asked for that. I suppose I could have changed that and put that into my API function. But yeah, it's quite nice that you could just put something on the web like that. And if you want, you can also do it in this way here. This is slightly different syntax, but the benefit is that you can set the parameters line by line, which might be to your taste. So in this case, survived again. So I might actually be able to go directly to that API. It's possible that I put it somewhere down here. Apparently not. Why don't I have a look for it? So with any luck, I should be able to find it in my files. So I will just show you what I'm looking at here. So I'm on my Wolfram Cloud account. I went into deployments, APIs. Let's see what I got. I mean, I've made a lot of junk, and I made this API a while ago. So it's possible that I won't be able to find it, but there you go. Titanic. So if I open that up, this is apparently the raw code behind the scenes. Let's see. But if I were to, let's see. Hopefully I can find my code that I wrote. I had a little line of code that gave me the stuff to add on to the end of the URL, so I wouldn't have to write it by hand, but apparently I have lost that code. That's excellent. Sorry, I'm just sort of getting ahead of myself here. Okay, so this is slightly later on in the talk. Okay, so with any luck, if I actually, you know what, I'm actually going to make sure I go to the URL directly if I can. So I'm just going to redeploy this actually. So if I go here, there we go. If I go here, and if I then grab my code here, sorry if this is a bit confusing. So what I'm just trying to emphasize here is that now that I've got my API at this URL, and I believe I made this public, so you may be able to go to this URL as well. If I then add a question mark and then my parameters and then give each one a value, so in this case, first class for the for the classification, let's say they are 80 years old, and let's say they are male, then if I evaluate that, just as you would, just hit enter as you would any other website, it gives me a result. So yeah, it's really nice that you can just, you can just create APIs like that. So anyway, that was a slight digression there. Let's go back into our Python notebooks for our final notebook, which is Wolfram Language and Python code in practice. So I just like to do a bit of mingling of the two and just show you, a bit of a more realistic example. It's not the best example, I have to say. It's a bit of a weird thing that we're going to be doing. What we are actually going to be doing is grabbing a data set and then simply swapping out all the values in it. So all the values are going to be GDPs, and I'm going to swap them out for populations. Why you'd want to do that, I do not know. And I'm probably not going to run all the code because it takes a little while to run because it's doing lots of individual calls. But nevertheless, I'd like to show you what that would look like. So now I'm pretending that I'm a data scientist who knows a bit of, I know a lot of Python, but I don't know much Wolfram language. But I'm desperate to grab one or two Wolfram language functions that I know will make my life a little bit easier. How would I do it? This is how. So first of all, I'm going to import the relevant libraries and begin my Wolfram language session. Then I'm going to grab my data. So my data is, you should have this too. It's in the additional files folder, and it's this World Bank GDP data. The actual data itself doesn't really matter. So let's just have a look at the first 5 rows, skipping the first 4 because they're just empty and not really useful to us. This is what the data looks like. I only care about the country name and the year, so I'm just going to drop these columns here, and there's one at the end, which is a load of junk as well. So I'm just going to drop that, drop these particular ones, and I'm also going to drop the world, because apparently that is a country in the list, which I don't really want. And also, just for this particular example, I'm going to reduce the data down to the first 5 rows. Not really necessary. But anyway, this is where the Wolfram language might come in. I might not know how in Python to interpret a string as a country, and so I can use the interpreter function from the Wolfram language. Or it might be that I don't know how to find out the population of a country from a particular date. Not a problem. We have entity value, and you can get dated populations from a particular year. Easy peasy. And in this case, I happen to be doing the rest in Wolfram language as well, but I might not have to, and I could also do that in Python if I wanted to. So there you go, started. So I've evaluated that, and now I can find the population of the UK in 2010 and double check that something that isn't a country isn't going to completely crash. There you go, just gives me not a number. And apparently the population in 2010 of the UK was 63.5 million. There you go. I don't think I've really put anything in it to, well, let's see what it does if I try and extrapolate. Okay, I'm impressed. So it turns out that we have already accounted for that, and apparently we do some extrapolations. So it turns out that in the year 2050, Wolfram believes that the population of the UK will be nearly 75 million. There you go. Huh, that's funny. And so finally, now that I've got my function, I can apply it to my data set. And now I pre-run this because it's slow as old wood. That's probably because of my terrible code writing more than anything else. But actually, I suppose it's probably because we're doing an individual call for every single country for every single year, which is probably not the best way of doing it. Entity calls are a bit fickle. You have to make sure you're not doing lots and lots of calls when you could just be doing one. So yeah, this is pre-evaluated, and what I've done is for the year in the range 1960 to 2021, I've asked for the GDP, and I'm applying an anonymous function where I'm grabbing the population of a row and at a given year. So I'm finding the population of Aruba in 1960, then 61, 62, and so on. Now, for many countries, there's not going to be any data. And now that's probably because in Wolfram language, we don't define this as a single country. I'm imagining it's probably considered to be a region or something. And so that's when I might want to check this. I might want to go back into my code and just see what that is. And in fact, if I were to copy this, I'm going to go back to wherever we were meant to be before. Okay, we were about here. So if I were to copy this like that, but ask for a natural language interpretation of that, let's see what we get. So there you go, that's why. So normally if I were to do, so this is with control equals, normally if I were to do a natural language interpretation, so what is France, it would give me an entity. This orange box here says France with a capital F is a country. And that then has things like, population. So that has things like population, various properties. Whereas this is not recognized as an entity, and that's why it didn't work. But nevertheless, yeah, we've now completed our little bit of code. So I can extract something for a particular country, for example, from 2 particular years, or I could produce a plot. So I could find the population of Aruba over time. There you go, very nice. So this is just my sort of finale, shall we say, to show you how you might be able to integrate Python and the Wolfram language in one place. In this case, from within a Python file, or rather a Jupyter notebook, rather than within Mathematica. So as you can see, I've injected some Wolfram language code here, but then the majority of the rest is Python.